It means there's a greater range of languages that can be recognized than can be decided. So power that means it's applicable to a greater range of languages, a greater class of languages. That's what power means. All right. Now, if you want a Turing machine to halt, that means accept or reject on all its inputs, well, that restricts the kinds of languages that it can recognize. Is that obvious? I don't know if that's obvious to you or not. Think about it. All right. So it's actually a consequence of a few lines about it. Alright, so let's try and prove that it's Turing recognizable. Okay? This language is Turing recognizable. So by definition, if a language is Turing recognizable, there is some Turing machine that recognizes it. And that in turn, repeating here, but again, more revision, and that means that the Turing machine accepts all the strings in that language. So in other words, we have to find, to prove that, we have to find a Turing machine that accepts all these. Right? So how to do that? Well, so we want to find a Turing machine. Let's call it U. U is actually short for universal, and I'll be saying a bit more about that, and complaining a little bit as well. But anyway, U for universal. It's a Turing machine, and its job is to recognize this language. Remember, to recognize means that that Turing machine accepts every string in that language, and that's it. No comment about what it does with strings that are not in that language. Recognizers don't talk about that. It's possible. In other words, with a recognizer, it's quite possible that that Turing machine, the recognizer, may actually loop when presented with a string that is not a member of the language. Right? Remember, in general, Turing machines can do three things, in a sense. They can accept, they can reject, or they can loop. Loop just means they never stop. Okay? So if you have a recognizer, it will definitely stop if the string is a member of the language. If you're told that if you know that the language is Turing recognizable by definition, so it'll definitely halt. It'll definitely halt because it will accept if the input string is a member of that language. But if it's not a member of the language, well, it's quite possible. Well, then there are two possibilities for that recognizer, that Turing machine. One is that it rejects, and the other one is that it loops. Okay. Now, if your Turing machine is a decider, it will. So, if the input string is not a member of the language, the deciding Turing machine will definitely reject. Okay? That it'll do. There's no looping. Deciders don't loop. Right? Okay, so we're going to create this Turing machine. We're going to call it U. U for universal. Explain in a minute what's universal about it. And its job will be to recognize this language. Okay, so in other words, if it sees this string, it will accept. U will accept. Right. Right, so the definition. So here's our standardized description, standard format description of an algorithm. In other words, Turing machine. Same thing. Algorithm, Turing machine. An algorithm is what a Turing machine does. Okay? Right. So this Turing machine on this input, right? That's the string that goes in. Your first line of the standard description is a description of the input string. So here it is. That's your input string, and M is a Turing machine, and W is just a string. Okay. All right. Then you describe the stages. Usually number them. Well, the basic idea of U, this so-called universal Turing machine, but it's just the Turing machine that's that we're constructing that will recognize this language. So the main idea of this Turing machine U is that it simulates M. Okay, so this string goes in. It contains the information about the Turing machine M. Now, don't be confused. We're talking about two different Turing machines, right? This Turing machine U, its job is to recognize this language, okay? And this machine, what it does is it accepts this string. Okay? Don't be confused. We're talking two different machines, U and M, and two different jobs. The job of U is to recognize this language. The job of M is to accept this string. Right? Much more restrictive. Much more restrictive. All right. Okay. So the basic idea is we're going to have this machine U simulate, behave in the same way as simulate machine M. So U will simulate M. So whatever M does, we'll have U do as well. Okay? That's what a simulator does. Behaves in the same way as. All right. So that's the essential idea. So extract the information about machine M here and use that to simulate how M would behave with this input W, the string W. Right? All right. Now, so if ever M, if it accepts W, well, then have U accept, right? And if ever M rejects W, then have U reject. Okay? Now, so what? So what? I mean, why is that a proof? Well, think about it. If M is accepting W, therefore that pair MW belongs to this language. Okay. I mean, what I'm saying now, and like next sentence or two, is sort of critical to the proof. So pay attention. Okay. All right. If M accepts this string W, well, then it's a member of this language. Okay? Now, if M accepts W, then U, because of this, U will accept. Right? U will accept. And so if this comes out to be accept, if M accepts W, well, then this member here of this language gets accepted by U. So if M accepts little w, then U accepts this whole string. Okay? And that's true for any MW, for any M, any W, but if that M, whatever it is, accepts W, whatever it is, then it'll belong to the language, and big U will accept it. Okay? So therefore this language, for every element of that language is accepted by U. Right? That's the punchline, what I've just said. So therefore that language is recognizable by U. Right? So okay, so that's the proof effectively. Alright, now a couple of remarks. Note what happens if M loops on W,